All right, this is my video submission for the Math 202 project. I chose to solve the MyOpenMath question 5 from the vectors in the plane section. I pulled the problem directly from the video project PDF. The problem reads, an airplane pilot wants to fly at a speed of 475 miles per hour directly east. However, there is a constant wind blowing 45 miles per hour from the northwest. That implies that it's blowing in the southeast direction. Determine the speed and velocity the pilot must fly to compensate for the wind and achieve the desired velocity, and complete the following with at least 2 decimal places of accuracy. The first part of the problem asks us to find the velocity vector the pilot must fly to compensate for the wind. The first step I took in solving this problem was, sorry. The first step I took in solving this problem was laying out a coordinate system with a x and y-axis being positive y-axis being north, positive x-axis being east, west and south being negative x-axis and negative y-axis. I then drew a red vector representing the desired velocity that the pilot wants to fly at 475 miles per hour east, and then a blue vector representing the wind vector at 45 miles per hour in the southeast direction. Assuming that the angle that the wind vector is coming in at is directly even between the two cardinal directions, there's the angle theta would be a multiple of 45, so in that quadrant we end up with an angle of 315 degrees. So for the second step of the problem, I decided to lay out the desired velocity vector, wind vector in numerical form, x and y components. The desired velocity vector ends up being 475, 0, when the wind vector ends up being 45 times square root 2 over 2, and then negative 45 square root 2 over 2. We get that from the rules of trigonometry that the x and y component of this vector are the multiple of the magnitude times cosine theta, and for the x component, and the magnitude of the velocity times sine theta for the y component of the vector. Moving on to how we end up finding the vector that the pilot must fly to compensate for the wind. We'll call that the correction vector, going from the head of the wind vector to the head of the velocity vector. That represents the vector that we want to find. So the correction vector plus our wind vector would equal our velocity vector. So we flip that equation to solve for the correction vector by doing the velocity vector minus the wind vector. Again, our velocity vector is 475, 0, and then our wind vector is 45 times square root 2 over 2, negative 45 square root 2 over 2. That equation ends up looking like this. 475 0 minus 45 times square root 2 over 2, negative 45 square root 2 over 2. We do that direct component subtraction, so our x component ends up looking like 475 minus 45 times square root 2 over 2, comma, and since it's minus a negative, we end up with a positive at 45 times square root 2 over 2. When you plug that into the calculator and give 2 decimal place accuracy, you end up with 443.18 and 31.82, which is makes sense graphically. As you can see, we're going to need to fly in the positive x and y direction as demonstrated by the vector here, the correction vector labeled on the graph. So that ends up being our answer for the first part of the problem. Then the next part of the problem, it asked us to solve what speed in miles per hour the pilot must fly. So to do that, we are just going to use the rules of converting from Cartesian to polar and solving our magnitude of our velocity vector. And basically to do that, all we're going to do is x squared plus y squared, the square root of x squared plus y squared. And that is the magnitude of our correction vector, and it gives us our overall speed. So we just plug that into the calculator. The square root of 475 minus 45 times square root of 2 over 2 squared plus 45 times square root 2 over 2 squared. That comes out to roughly 444.32 miles per hour, giving us our answer for the second part of the problem, which is the speed. And then following that with similar conversion from Cartesian polar rules, we want to find the theta for the velocity vector, and that ends up being inverse tan y over x, which in our case is inverse tan 45 times square root 2 over 2 over 475 minus 45 times square root 2 over 2. And that ends up giving us 4.11 degrees north of east, which is seems pretty accurate considering it's not a heavy correction graphically. And this isn't exactly to scale, but I still think you can visualize the how that kind of makes sense. So that is my entire video submission and just me going over my work and how I solve the problem. Thanks.